In this video, we are going to review the basic components of wood frame construction. The reference for this video is Marine Corps Reference Publication 3-40 Delta.3 Carpentry. The first component of any kind of wood frame construction is a foundation. There are three types of foundations that we use. The first is a continuous foundation. A continuous foundation extends all the way around the perimeter of a building and is usually made out of concrete block or poured concrete. The next type of foundation is a column or pier foundation. In a column or pier foundation, columns or piers made out of wood, masonry, or metal support the building. It takes less time, less materials, and less labor to construct a column or pier foundation, and the spacing is determined based on the weight. One thing to remember is if you are using wooden piers, that if they are greater than 3 feet above the deck, they have to have some sort of diagonal bracing on them to support them. The last type of foundation is a continuous mud sill foundation. This is used for light expeditionary shelters or structures, and is comprised of simply putting laying dimensional lumber flat on the deck. The next component is the sill. The sill transfers the weight of the building to the foundation. There are two types of sills that we generally use. The first is a box sill. A box sill is used with a continuous foundation and is simply dimensional lumber laid flat along the foundation. Usually you want to use some sort of pressure treated material and place a vapor barrier or a moisture barrier, plastic or tar paper, between the foundation and the sill. The next sill is the built-up sill. A built-up sill is used with a column or pier foundation, and it transfers the load of the building down to those piers. It can be either made out of one large piece of lumber or dimensional lumber laminated together. An important thing to remember about your sill is that it must have bearing. Bearing means that the weight is transferred straight down in a continuous line from the sill to the post. You do not want to attach your sill to the side of the post, thus by relying on the fastening devices to transfer that load down to the post. General rule of thumb is if you can stack it like blocks and gravity can keep it in place, then you're probably on the right track. Another thing to take note of is the way that the joint at the corner here is staggered on a built-up sill. Then of course, with the continuous mud sill, we already have our mud sill. Our sill is our foundation. In some cases, the distance between two sills is too great for a single joist to span. In that case, we use what's called a girder. A girder is similar to that built-up sill in that it can be made of one single piece of lumber or several smaller pieces of lumber laminated together. It is supported by columns or piers, and any splices in the girder must be supported by a column or pier. The spacing between the column and piers is determined by the weight which will be supported, and the girder must have bearing on that column or pier. More information about the nominal size of girders required and the length that they can span can be found in Table 6 Tack 1 in Chapter 6 of the Carpentry Manual. The next component is the floor joist. Floor joists transmit the weight of the building through the sill to the foundation. They're usually made of 2x or 3x material laid on edge and are generally laid out 16 to 24 inches on center based upon the length of the span and the size of the floor joist. More information about span length and joist size can be found in Table 6 Tack 2 in Chapter 6 of the Carpentry Manual. So for example, on this shed here, we have a 10-foot span, and we're using 2x6 joists spaced 16 inches on center. In the main part of the building here, we have a 10-foot span, but we are using 2x8 floor joist spaced 24 inches on center. And in the extension on the back of the building here, we are using 2x12s spanning 16 feet, 24 inches on center. Another thing to remember with floor joists is, just like the girders and the built-up sill, you have to have bearing. So that floor joist must be resting on the sill or on the girder, unless you are using some sort of commercial metal joist hanger or fastener. Floor joists tend to warp and twist over time. So to mitigate this and to stiffen the floor, we use what is called bridging. There are two types of bridging. The first is cross bridging. Cross bridging is made out of 1x3 or 1x4 material cut to fit diagonally in between the floor joists. The top of the bridging is nailed first, then the subfloor is installed to allow the floor joist to settle to their final position before nailing the bottom of the cross bridging. The second type of bridging is horizontal or solid bridging. With horizontal or solid bridging, you use the same size material that the floor joists are made of and cut the pieces to fit in between the joists and nail them in a staggered row such as this. The rule is any span greater than 8 feet gets 1 row of bridging, and any span 16 feet or greater gets 2 rows of bridging. Our next component is the subfloor. Subfloors are generally made out of plywood, 3/4 inches thick or greater. However, it can be made out of dimensional lumber such as 2x material, 2x6, 2x4. The plywood is laid out in a brickwork pattern so that the joints are staggered to increase the strength. Also, the plywood is laid out in a manner so that the long edge of the plywood covers as many joists as possible. Now let's take a look at the walls. Walls are usually made of 2x6 or 2x4 material, depending upon the requirements of the building, and can be classified as either load-bearing or non-load-bearing. Load-bearing walls are usually found on the exterior of the building and support the weight of the roof, transferring the load through the floor joist, through the sill, to the foundation. Non-load-bearing walls are usually found on the interior of the building and serve as partitions breaking up the floor plan, but don't really support any real weight. The components of a wall are the sole plate, which runs along the bottom of the wall, tying all the studs together at the bottom. The top plate, which runs along the top of the wall, tying all the studs together at the top. A common stud, which are typically spaced 16 or 24 inches on center, depending upon the requirements of the building. Anytime you have an opening in a wall, you're going to have some additional components. This stud here is called a trimmer stud. The trimmer stud runs along the edge of a window or doorway from the sole plate all the way up to the header. The header is usually made of 2x material. The thickness will vary depending upon the length that is required to span. So for example, for this door, we're using a 2x6 header. For this hallway opening here, we have a 2x12 header. The header is made by taking two pieces of material, in this case 2x6, laminated together with a piece of plywood in the center in order to make it the same thickness as our wall material here. Above the header is called a cripple stud. The cripple stud transfers the weight from the top plate through the cripple stud, through the header, through the trimmer stud, to the sole plate, all the way down to the foundation. On the corner of a building, you're going to have what's called a corner post. Corner posts are built up from two common studs with filler blocks in the center. The corner post helps to strengthen the corner of the building, and it also provides a nailing surface on the interior of the building for the interior sheeting, whether it be plywood or drywall. On load-bearing walls, you're going to have a double top plate. The double top plate ties in the joints of the top plate. It overlaps the joints of a top plate, as you see here, and it also ties in the corners of the building at the top of the wall. Next, let's talk about wall bracing. Wall bracing strengthens and stiffens the walls, and we have several different methods to achieve that. The first one is lead-in bracing. Lead-in bracing runs diagonally from the sole plate all the way up to the top plate, and is usually made of 1x4 or 1x6 material. In lead-in bracing, the studs are actually notched out in order to let the brace into the wall. The next type of bracing we're going to talk about is cut-in bracing. Cut-in bracing uses the same type of material used for the studs themselves. In cut-in bracing, the brace material is actually cut and placed in between the studs. So instead of the studs being cut like in lead-in bracing, in cut-in bracing, the brace material is cut and put in between the studs. The next type of bracing we're going to talk about is metal bracing. Metal bracing is bands of metal that are strung diagonally from corner to corner, and then they are nailed in every place they cross a stud. These horizontal blocks that you see in this wall here are what we call fire blocking. Fire blocking is installed in a similar manner to the solid bridging that we put into our floor, and it does serve the purpose of helping to stiffen the walls, but more importantly, it prevents fire from moving up through the wall in case of a fire. If your exterior sheeting is at least 5/8 inch thick, all other methods of bracing can be omitted. Wall sheeting is laid out in the same way that the floor sheeting is, with the joints staggered and the long edge covering as many studs as possible. This is going to make your walls strong and sturdy. However, in some cases, your plywood is going to be your exterior surface. In those cases, it is better to run the plywood vertically in order to eliminate the gaps in between the plywood. Those gaps fall on a stud, and it eliminates the gaps and makes your structure more weather tight. Now let's talk about roofs. The simplest type of roof is a lean-to roof. A lean-to roof has a single surface that slopes away in one direction. It's the simplest type of roof to make. You'll see these on sheds, on additions or porches, such as you see right here. The next type of roof is the gable roof. The gable roof is very common. It's economical to make and very easy to construct. It has two sides that slope away from a single ridge. Next is the hip roof. A hip roof has four sides that all slope away from a central ridge beam. It's the strongest type of roof because each side slopes away, so that whenever the wind hits it, it's hitting a slope side instead of a flat side like you would in a gable roof. And then the last type of roof is an intersecting roof. An intersecting roof forms a valley right here whenever two different roofs meet at a perpendicular angle. So here we have this gable roof meeting this hip roof, forming an intersecting roof. When we peel back the roof sheeting, it reveals our two different types of roof systems. The first one on the main building is a rafter system. On the shed here, we have a truss system. Let's talk about the components of each of these roof systems. For the rafter system, our highest component at the top is called the ridge beam. The next is our rafters. We have a common rafter which runs perpendicularly from the top plate all the way up to the ridge beam. It's called a common rafter because you're going to find it in every type of rafter system roof. If you have a hip roof or a valley roof, you're going to have some additional types of rafters. So in a hip roof, you're going to have this hip rafter that runs diagonally from the ridge beam down to the corner of the building. And then in a valley roof, you're going to have the valley rafter that runs diagonally from the ridge beam down to the interior corner along that edge, along the line where those two roof surfaces meet. Then you're going to have your hip jack rafters. Hip jack rafters run perpendicularly from the top plate to that hip rafter. And you're going to have valley jack rafters, which run perpendicularly from the ridge beam down to that valley rafter. The other component you see here is called a collar tie. A collar tie ties the tops of the rafters together, helps to add some strength and stability to your roof system. And then down at the bottom here, running along the outside of the rafters, down at the end is called fascia, and it ties the ends of the rafters together and helps to close in the ends of the rafters to close in the rest of your building. Now let's take a look at the truss system. Trusses can be ordered commercially, or you can prefabricate them at your shop before you head out to the site. And they're made up of an upper cord, this piece up at the top here, a lower cord, webbing, and then plates. The plates can be either made of plywood or they can be metal fasteners nailed or pressed together. Trusses are convenient because, especially if you order them, they arrive and all you gotta do is set them up. You don't have to do any cutting or anything like that. If you have to make them though, it can be time consuming to build a jig, cut all the pieces, and then all the nailing that goes into nailing those plates together to form the truss. But that's a truss system there. Then our last component is our roof sheathing. Just like the wall sheathing, you typically want to use plywood that is 5/8 inch thick or greater. It's going to be laid out the same way as the floor and the walls were, staggering those joints in that brickwork fashion and spanning the long edge across as many rafters or trusses as possible. Then you can put on either an asphalt shingle roof, a metal roof. I've done fuel bladder roofs, water bladder roofs, whatever you can do with the materials you have available to you in order to make that roof watertight. This has been a basic overview of the components of wood frame construction. For more information about this subject, please read Marine Corps Reference Publication 3 TAC 40 Delta .3 Carpentry. For more information, visit the Marine Corps Training Information Management System, or MCTIMS, select Training Resources, and then select Search.